Hey, welcome here, and we're off to another online lab here. It's actually one of my favorite labs. It's one that I hope will come across on the video. That it's kind of a fun lab. I wish more that you were actually in here playing with this equipment, because we're going to have a lot of wires and a lot of connections, and it's that experience that is really helpful. But also, it is really just kind of a fun lab. I like to say we are going to build a voltmeter. Now, technically, it's a potentiometer, and we'll talk about that. There's a slight difference between a voltmeter and a potentiometer. But for the moment, let me just say we're going to make a homemade voltmeter. All right, and then, like I said, technically, it's a potentiometer. So more on that to follow here. But it's really kind of fun. And so we've got some wires and equipment and a lot of ideas about our circuitry that hopefully, like I said, we'll come across here. And so if you've got your lab manual, although I'm going to change it significantly, we have newer equipment than what this lab manual was originally designed to portray. And so if you're looking at the first couple of pages, and so let me encourage you to start there. There's quite a few pages, and so read starting at page 12 and going through 12, 13, and into 14, and I'm going to highlight those descriptions as we go along in the lab. So let me not explain all those pages quite yet, but I think it would do you good to read it first. So do that first. And then we'll start, excuse me, on the on the 4 steps here. But even the last one, we're going to just kind of skip over, which I'll explain why. And so it's really 3 steps. And so we've got these 3 steps here. And so the first one says here, it says calibrate and build a 2-meter potentiometer. All right, so let me do that with you, okay? I'll do the equipment here, but I'll begin by drawing some pictures here on the board. I want to show you the idea of the potentiometer, and particularly the 2-meter potentiometer. So the big first step of the 2-meter potentiometer is to get a power supply that has a known voltage, and we're going to use a known voltage of 2 volts. The 2 volts will make sense because it goes with the 2-meter potentiometer. Oh, watch this. What we're going to do is then hook our 2-meter potentiometer to a nichrome wire that is 2 meters long. And so I will represent it as a resistor here, but I'll make it really long to hopefully indicate to you this is the 2 meters worth of wire. And if I can kind of match what your author has in his circuit diagram, because like I said, I'm going to do a number of changes because of our newer equipment here. He calls this connection A, and over here at the other end of the 2-meter wire, connection B, and then he just circles it around. Okay. And it turns out that we really won't need to know what the total resistance of that wire is, but I'm going to go ahead and put this equation up here that we've been learning and learned in the chapter 27, Ohm's law, that the resistance of a wire is what it's made out of. So this is a nichrome wire. Its length, which is 2 meters, that's why we call this the 2-meter potentiometer, and then its area, which we won't bother to measure the area because, like I said, we don't really need to know that number exactly. That's one of the neat things about this lab. But to show you the equipment, here's my 2 meters worth of wire. I'll hold it up here, and starting with this blue connection, that would be A. And you can see the wire laying on the first meter stick, and then it comes over to this metal connection. And so this is a nice thick piece of metal, where then more wire continues on another meter and comes back to here. So that's why we call it a 2-meter potentiometer. It's 2 meters. It's actually 1 meter twice. And this end over here, where it's connected together, the fancy word would call this a bus. And so anytime we have a piece of metal that connects one electronic to another electronic, we refer to it as a bus. I think I used that phrase when we did our equipotentials. So we have a bus in between there, but we're not even going to really pay attention to that. It's just that we actually have a wire that's 2 meters long. And so let me just go ahead and connect it. And so before we started the video, I was adjusting the power supply. It looks like I'm a little shy, there we go, of 2 volts. And so it says it is 2 volts. Let me pause for a moment and take this as an opportunity to use the handheld voltmeter. This voltmeter built on here is not quite as good as quality as this, but it's pretty good. So I bet even it says 2 volts, it probably is. But if you can see, it's only to 1 decimal place. This will give me 3 decimal places. In fact, it's almost too accurate because I won't be able to adjust the knob to that much accuracy. But let's see if it would agree with the handheld one. But this will give me a chance to point out about voltmeters. If you remember last week in the Ohm's law, I said voltmeters and ohm meters are hooked up a little different. Voltmeters are the easy one. Voltmeters are hooked up in parallel. So if I grab 2 wires, and so here's 2 wires, and I want to measure the voltage of something, so let's say this power supply here, so I'll connect it to here and to here for just a second. Maybe I'll leave it up for the lab, who knows. But this is what I wanted to show you, which is really kind of the bummer part. You guys aren't here in class because it's good to get some practice with this. This is called a multimeter. It's called a multimeter because it measures many different things. Let's see, it measures voltage, it measures current, it measures resistance, it measures diodes, it measures conductivity, and I think that's the end of that this one does. Okay. The dial in the center is pretty self-explanatory. You click it twice and it goes to V for voltage. Okay, and so there's my voltage. And of course, then I just plug it in. But this is the part I want to show you, even though you're not going to get a chance to hand-hold these this semester. But there are connections here, and we got to connect 2 of them, but there are 4 connections, and that can be a little confusing at the beginning. And so with some experience, you begin to gain the idea of which ones do I connect it to. Well, it depends what you're trying to measure. Are you trying to measure current? Are you trying to measure voltage? So I'm trying to measure voltage. So one of the ones I like to say do first is the one that says COM. It stands for common. What that really means is no matter how you're using this handheld multimeter, we often call it a DMM, digital multimeter. No matter how you're using it, you will always connect to the common one. So that's the easiest one to connect. It's the second wire that could go here or here or here, depending on how you're trying to use this multimeter. Now I'm trying to use it as a voltmeter, so you can probably guess then that the V for volts is what you would want it, which is exactly true. You can also see the symbol for ohm, so I would connect it there as an ohm meter, and the symbol for the diode, so I'd also connect it there if I were measuring diodes. But today I want volts. Which, by the way, means these other 2 would only be used for an ammeter, and we'll get our chance to do that. All right, so this says that the voltage is 2.033 volts, and so it is within at least 1 decimal place, 2.0. Now, with that in mind, I want to make sure that it is 2 volts when it is actually hooked up. And that's part of the lab today, is when you hook up a power supply, things can change a little bit. And that's the big point to see in step 3 here. So even though it says 2.033 volts, I really am interested in what does it say once I hook it up and it's running. So if you come back to this picture here on the board, see, I want 2 volts when it's actually hooked up. So that's why I'm going to take my power supply, and looking at my power supply, it says negative. Looking at my picture, whoops, it says negative, and it says hook this to point A. All right, so that'll be point A on my 2-meter potentiometer. And the other one, the positive side of the power supply, says go to point B. And of course, you could imagine that now current starts flowing in this homemade voltmeter that we're trying to build. In fact, I don't know if you noticed, but this number actually went up. See, now it says 0.18. That's how much current is flowing out of it, right? Before I hooked it up, it said 0. So let me come back over here and see if I still have a reasonable amount of voltage. And you can see that it changed, but only in the 3rd decimal place. These are pretty good power supplies that once you hook them up, as long as you're not talking about anything more than about 2 or 3 amps, and I'm way lower than that, they won't change their voltage. You start getting to 2 or 3 or 4, and in fact, they won't even put out more than 5. They just give out. And so that's what the electronics is designed. Things can change. So I would say at this point I'm not stressing the power supply at all. And so that's why it didn't really change. It really is supplying me with 2 volts. All right. So I'll leave this hooked up just for the sake of being hooked up. That's not really the main part of the lab. The main part of this lab is to build our own voltmeter, our own potentiometer out of this wire. And that's what's kind of neat about it. We're going to actually make a voltmeter, a homemade voltmeter, using just a wire. And so this goes way back to people like Kirchhoff and Wheatstone and some others who were just kind of thinking about this new world of electronics 150 plus years ago. And so this is what they're kind of tinkering with. And so like I said, that's why it kind of makes it kind of a fun lab. All right, now how does this homemade voltmeter actually work? Well, let's come back to the board here, because maybe now you begin to see why the creativity of having 2 volts as well as 2 meters come into play. Because of this resistor right here, and because of Ohm's law, V equals to IR, this 2 volts of push, and then this is being dissipated. And so remember, the sum of the voltages around the loop have to be 0. So if my power supply goes up by 2 volts, then there must be a decrease of 2 volts as I go from B to A. Or put the other way, there must be an increase of 2 volts as I go from A to B. So spread out over this wire is that 2 volts. So if I'm beginning to make any sense to you, if I went halfway, I would be at half of the 2 volt increase. This should be at 1 volt. Let me give it a try here. Let me come over here and take this voltmeter here so you can see it, and let me plug it in to this bus that is halfway, which is 1 meter. If everything's hooked up right, this should be saying that point is 1 meter, and sure enough it is. Same logic. Watch this for a moment. What if I were to look at a point right here that is a ½ meter? What would I get? I'm hoping you can see, since we've got 2 volts spread out over 2 meters, I would get a ½ volt. And I probably should have put it here. This 1 volt was at the 1 meter mark. And so now you can begin to see that if I look at 1½ meters, I should be getting 1½ volts. And so this is how our homemade voltmeter is going to work. It isn't going to have a display that tells us what the voltage is. It's going to have a location on the wire. Each location on this nichrome wire is a different potential. And so that's why it's called a potentiometer and not a voltmeter. Okay? Okay, it works a little different. It takes the potential, the 2-volt potential, and spreads it out over the wire. And so as we use this homemade voltmeter, we're going to keep in mind that different points along this wire represent different voltages. Watch, I'll show you. Let me disconnect it here, and let me put something that I can actually touch the wire. And so this little slider works nice. And let me just tap the wire, and I'll actually touch it right here at 1/2. And then hopefully the voltmeter says 1/2 volt. Sure enough. Or the potentiometer is giving me 1/2 volt. I'll move it to the other meter. So this meter over here is 1 meter, and then this would be 1/2. So I will come to 1.5 meters and touch it. And sure enough, it says 1.5. Now, I did notice it didn't say 1.5 exactly. And sadly, this is where our homemade voltmeter is not going to be as good as quality as we would like. Remember I said that the voltage is distributed evenly, and that used to be true many years ago. But over the years, I think because students have moved our metal piece and slided it on the wire's kind of scratched and scraped off, and it doesn't have this uniform area anymore. And so because of that, our homemade potentiometer is not as accurate as we like to claim it is. It's just not very uniform. And also students hook it up wrong and they've overheated the wires, and that kind of damages them. Sometimes I'll come across and I'll look at the wire, and the wire's like glowing red hot. It looks like somebody's got a toaster, and this thing's like up to 7 volts or something. And I'm like, well, no, wait. And so we have some damaged equipment. However, despite its inaccuracy because of the damaged equipment, it is still one of my favorite labs. It's kind of neat to see. So like I said, I hope that will come across. I really like kind of just building my own voltmeter here. There's just something quite fascinating about this. Nothing fancy, no high tech, just really nice way of getting it. Now, let me continue on then. Because now that you understand kind of the basic idea of the potentiometer, how do we then use the potentiometer to measure something? And here's how we're going to use it. We are going to take whatever it is we want to measure. And I will tell you that our first step is to measure one of these, let me change my drawing a little bit. One of these just standard Dcell batteries and measure its voltage. So I wanted to kind of draw this in my picture so I could put the little knob out there. Because if you don't already know about D-cells, the little knob part is the higher potential, and that means the flat part of the battery on the other side is the negative. I'll hold one up here so you can see it. Here's a standard D-cell battery. There's the little knob on the top. It even says plus on it, so there's the plus side. And then the other side is the minus side. So this is the low potential, this is the high potential. And it even says here that this is about 1.5 volts. I think it's like, we're going to get a little higher than that because of the chemicals used by Dcell. It's an alkali battery, so they use the alkalis. And so probably 1.55, 1.6. Let's just measure it, and that's our goal here. And so how do you measure it? Well, it works like this. First of all, you connect the negative to the potentiometer. Okay, so maybe I'll start there. And so here's mine for the equipment today. This one I put in a little battery holder, and it's got easy banana jacks for me. And so here is that battery. Let me do that first thing I said. Let's hook the negative of my D-cell that I'm trying to measure to the negative of my homemade voltmeter, my potentiometer. Okay, now here's the main idea. I'll show you a picture first. But if I were to take another wire, and I'll leave it just kind of free for a moment, and I were to touch it somewhere on my potentiometer, and for the sake of discussion, let's say I touch it right here at this 1 meter mark, which represents 1 voltage. What this is saying is there is a battle going on. This 1 volt wants to push current this way. This battery wants to push current that way. And they're battling each other. And whichever one is bigger is going to win and push the current. So in this case, I said a moment ago that the voltage of these Dcell batteries is a little more than 1.5. Let me just write 1.5 there for a moment. Clearly 1.5 is greater than 1.0. So, as these battle each other, this one is going to win. And the current is going to go that way. So, I am going to hook a little instrument that's called a galvanometer. This is what our galvanometer looks like. And the galvanometer has a little needle that if the current goes in one direction, the needle moves. If the current goes in the other direction, the needle moves the other way. So when I set up my battle, I can tell which one is winning. And I can tell then which one is stronger. So I will set that up in just a second, but here's the final step. The final step is to find the magical point where the galvanometer would not deflect. Because as I touch it at different locations, when the voltage of my homemade voltmeter is the same as what it is I'm trying to measure, then when they match, there'll be no deflection. And so this is what we're looking for. This is an instrument called a null detector. In other words, if you're getting a reading, you're not quite adjusted right. Keep adjusting until you get no reading. Okay? That is no deflection. Okay? And so when you get no deflection, that's when it's working right. Now, how would you voltage? Well, like I said, you would just read where on the 2 meters, or the 1 meters, where you're touching it, and that would be the voltage. You probably then are expecting, and at least I hope you are, that they should balance each other when I touch it right about there. Because I know that these Dcell batteries are in the neighborhood of 1.5. But even if I didn't know that, that's what I'm going to discover here. And so let me finish setting this up, and we will now have completed step 1, and that is build your homemade voltmeter. All right, so let's see. I've got the battery here. I think the part I'm missing is 2 wires. The first wire, let me get a little longer one, is to say let's come from here to the galvanometer. And then from the galvanometer to, and this is where I will touch it wherever seems necessary. Now I will say that my galvanometer has one more added nice feature. My galvanometer doesn't actually work unless I push this button. This is a connection button. And so you can see it. Maybe I'll kind of hold it this way. And let me just hook it up what I know is going to be a wrong reading, but I'll just to illustrate, show you, that if I were to put this right here, which I know is 1 volt on my 2-meter potentiometer, and I know that my Dcell battery is 1.5 volts, let's just see what happens when I push the button on the galvanometer. And so I push the button, whoa! Now, you'll see it moved positive. Here's what that tells me. What that tells me is that this device that I'm trying to measure is much more in potential than where I touched it. I touched it at the 1 meter. So that would tell me right now my battery is more than 1 volt. Of course, not a surprise. I already told you it was going to be more than that. But that's how we're going to actually do it. And so I would say right now I'm done with step 1 where it says build yourself a homemade voltmeter. So let's go on to step 2. Now that I've built it, it says go ahead and do this. Grab yourself a new and an old battery and measure the voltage from it. Technically it's measure the EMF. Now let me pause right there here, because here's where we begin to see the value of a potentiometer versus a voltmeter. Let me add to our knowledge, and you'll see this well covered here in chapter 28 this week, that you can think of a battery this way. A battery has inside of it a chemical reaction that creates what we call an EMF, an electromotive force. This is the voltage we get from the chemical reaction. For these guys, these Dcell, they are alkali, okay? And so the alkali, whatever they use, I'm not sure, and they really don't want people to know, this is their chemical formula, okay? But there is a chemical reaction. The easier one to explain is probably the one in your car battery, because it goes back so many, 150, 200 years. It's just the lead and sulfuric acid and the lead oxide that react. But here's the interesting thing about a battery. Once you build the battery and you create the voltage in a chemical reaction, it then has to flow through the battery to get out. And we can model that as a little bit of resistance. We like to call it an internal resistance. And so I'm going to put a lowercase r for that resistance. And what I'm trying to say is in this battery, I have a chemical reaction, that's the EMF part of it, and then a resistance. And so if I am using a battery, I will create a certain voltage, but remember Ohm's law, there will be a voltage loss as the current attempts to get out. So what we call the terminal voltage, let me call it V sub T. That is, what voltage would you get if you just connected a voltmeter to the terminals of the battery? I'm hoping you would see that it would be the EMF minus a little bit. And I say a little bit, but it could be a lot. It really depends on what these numbers are. One number is how much current are you asking from the battery, and the other one is how much internal resistance. And you could see that the goal of a good battery would to have a low resistance. And so yes, most batteries, and practically all new batteries, have a very low internal resistance. They're usually made out of these chemicals that not only react, but they conduct really well. But here's the sad part. As you start to use up the chemicals in the battery, they become a different chemical during the chemical reaction, and they don't conduct as well. And so what happens is this number tends to go up and up and up as the battery gets older and older, or more used. I shouldn't say older as much as used and used and used. So that's this whole idea, and we're going to study this in great detail in step number 3 to help us kind of understand batteries and EMFs and terminal voltage and internal resistance. But getting back to our problem at hand, here's what we're going to do. This is why this was so important. Let me come back to this drawing. Do you remember I said to use the potentiometer correctly, we want to take a reading when there's no current. No current. Let's come back over to this statement. If there was no current, and so if the current is equal to 0, you would get the terminal voltage equal to the EMF. So that's the only time that the terminal voltage would be equal to the EMF. And so you need an instrument, and this is where the potentiometer differs from the voltmeter. A potentiometer actually then is a creative way of measuring the terminal voltage, but when there is no current flowing in the battery. Because if I did something like this, if I just took my voltmeter and I came over here and said, hey, let's measure the voltage of this battery, and I just touched one end to the negative and one into the positive, a small amount of current actually has to flow out and go through my voltmeter. And so we like to say, because of that, voltmeters are not as accurate as potentiometers, because they actually force what you're trying to measure to draw current out of it. And so whatever you're trying to measure, you end up changing it because you've got to send some of your current to your voltmeter. Now, I say that with a little bit of caution, because 25, 30 years ago, that would have been important. Today's voltmeters, the amount of current that actually flows through here with today's modern electronics is so incredibly small that in the world you guys are about to enter and graduate, there's not usually much of an argument that potentiometers are better than voltmeters. And so I should say that up front. Now, if you wanted something real accurate, and so for those of you going into the science, the potentiometer may be the way to measure something extremely accurate that you couldn't get with the voltmeter. Now, for most of you that are going into engineering, it's close enough, it'll work, and that's really what you want for engineering. And it's like we want it to work. How it works, why it works, what percentage does it work often isn't as important as, hey, it works. And so there's kind of that subtlety there. And I wanted to point that out because I think that's one of the questions that you have on the discussion questions here. All right, so with that in mind, I think I can actually now make a measurement and give you something that you can actually write down. And so instead of just sitting there and hopefully learning, you can actually measure something here. So here's what we're asked to do. And I'll put it right here so you can write it down and have something to turn in. It's step number 2. It says here, what is the EMF of your new battery? And what is the EMF of an old battery? And we're going to extend that into step 3 here. So let me give this a try. As I pointed out, I already have a new battery connected here, and I'll just check it again. I have my galvanometer hooked to a place on the potentiometer of 1 volt. And so if I push in this button, it deflects very quickly, telling me this is not the right spot. It's also telling me that the potential of this one is much higher than this one, and this is 1 volt. So I need to go to the higher side. And this is where this little nice tap switch comes into play, because it can just ride along the top. And I think this will be wrong too, but again, to illustrate it, I can touch my potentiometer at 1.4 meters, so that'd be 1.4 volts, and I can push in the switch here for the galvanometer. Here I go, 1, 2, 3. Oh, there it goes, and went positive. Now, I'm hoping you can see it went positive, but at a much lower rate. It barely moved positive. So I guess that would tell me that I'm getting close. I'm still too low, and so I'm going to move this one. And just for illustration purposes, I'm going to go too high. I'm going to go to 1.6 meters. I hope that's high enough. Like I said, it's a Dcell one, so they tend to be a little bit on the high. But this would be 1.6. Let me push in the button and see what happens. Oh, it barely moved negative. So I didn't illustrate it real well. Let me go to 1.7. All right, so I'm going to go to 1.7 and touch it and push it and see how it goes the other direction. And so now the voltage on the potentiometer is a little bit stronger. And so my goal here is to try to find where it balances. And sadly, the shaking of my hand kind of affects it. So I'm gonna have to lay it this way. I don't know if you'll be able to see it, but I'll touch and push, and that goes just a hair positive. So I'm gonna go to about 1.6 and touch it and push, and that's going a hair negative. And that's going a hair negative. And that's going a hair negative. Oh, and that's going a hair positive. Oh, that might be it. All right, so it looks like I am touching it at 1.569. And so I would write down 1.569 volts, because that is 1.569 meters. And so finally I'm there. I don't know why, but like I said, this kind of gets me excited. I've actually made a voltmeter. I've got nothing but a couple of wires here and a battery, and I can now read the voltage on this battery. And that is the EMF. That is what we would say the terminal voltage without any current. This is the voltage I would get during the chemical reaction. All right. Then it says try it with an old battery. And so to separate our new batteries and our old batteries, we mounted it inside here in a big classroom. When everybody's in here, there's so many batteries floating around that it's easy to get these confused. And so this is how we've dealt with it in the past. The ones that have gone dead over time, we then mount inside this little box. So this is a dead battery. But let me just come back to this picture. Here's what I really want to illustrate here. This is part of the lesson of chapter 28. Dead batteries are dead in a reason that you may not really have expected. In other words, we have used most of the chemicals in here, but there still is some. I'll just say 10%. So 10% of the chemicals are still there. And so remember that the voltage is how much energy you get per electron, per charge. So even though you have less of them, the ones that do react actually have the same amount of energy. They have the same voltage as they did back at the beginning. So what makes an old battery an old battery? What makes an old battery not a useful battery? And the answer is here. 90% is now part of this resistance. And so even though you're getting the same voltage, if you will, from the chemical reaction, the EMF is still the same. The terminal voltage is not when you are actually using the battery. And so that is a small and important subtlety that I hope I'm communicating with you, not only here in the lab, but also in the lecture when we do this. I think it's like section 1 or 2 in the book. Although I think I'm in the video lecture, I hold off to the very end. So I do all the circuitry stuff and then I hold off on this discussion because I don't think it's a good way to start the chapter. But nonetheless, it's an important part of this. So I'll say it again just to emphasize it here. That we will hopefully see that an old battery is old not because the EMF has changed. It's because the internal resistance has gone up. And that's what I want to get across here. Because watch this. And I'll have to convince you this is an old battery, and we'll do that in step 3. But let's measure the EMF of this old battery. All right, so what I'm going to do is the same type of logic, except now I am going to replace my new battery with my old battery. All right, so here is my old battery. And maybe just to kind of give you the same idea, I'll hold up the galvanometer. I'll put it way over here on the 1 volt for the potentiometer. And I will do the tap switch, and you will hopefully see it goes way positive. And so even though this is an old battery, you might be surprised, and that's kind of the main point here to show you of what the EMF actually is. So I will then touch at 1.4 and see it still goes positive. So even though I'm calling this an old battery, although I have yet to demonstrate to you it is an old battery, but it is. That's coming. 1.4, I'll even go here to 1.5. I'll touch 1.5 and you'll see it goes positive still. And so like I did before, let me hold it down here and get a more accurate reading so I don't shake it. Let me come to 1.55. It still goes positive. 1.56 still goes positive. What did I get before? 1.56, okay. 1.57. Barely goes positive. 1.58. Oh, this one's still going positive. 1.59. Okay, didn't go positive, but didn't go negative. How about 1.60? Now that's negative. And so I'm going to go back to 1.590. And I like that. So here's what I'm going to say. I'm going to say, even though it's an old battery, I get a voltage of 1.590 volts because I'm touching it at 1.590 meters. So again, let me say it. I actually built my own voltmeter here. I built a voltmeter, technically a potentiometer. That is, I have measured the voltage of this battery when no current is actually flowing. That's the neat thing about this. But also, did you see this? Did you see that voltage? Now it's a hair higher, but let's ignore that for just a second. I'll come back to that in just a second. But I'm trying to convince you that the old battery still has the same EMF as the new one. Now, you might say it's a hair higher, but I think it's just a different manufacturer. I didn't look at what kind of battery it is. And so I think it's an energizer in there. And energizers use a little different chemical mixture. I don't know what they use, but I do know this, that over the years, when I measure the energizers one, the EMF is about this number, 1.59, whereas the Dcell ones are about 1.57. And I'm not saying one is better than the other. That's such minor compared to how much chemicals they put in them, which is why you can get those Dcell ones that are regular Duracells, which are actually really long lasting in themselves. But then you get those special ones. I think they got a blue band on them and they like have a lot longer lifetime too. And that's because they put more chemical, not that they put more voltage in there. Okay, they just more chemicals. They pack in a little tighter. I think, like I said, they don't like to share any of that information. They're trying to run a business and they don't want Energizer to copy them, and obviously Energizer doesn't want Dcell to copy them, and so they're in a competition. And as a side note, a good competition not only does that improve battery life, but that improves competition for salaries. And years ago when I worked for Boeing, I couldn't tell you how many people would leave Boeing and go to Rocketdyne, and then from Rocketdyne over to Grumman or Northrop, and then back and forth. And so they would take their knowledge and their information and they would go to the highest bidder. And if somebody's willing to, hey, you're paying me $60,000 this year, but hey, now next year this guy will pay me $80,000, I'll go there. And then they want me back, so they'll pay me $100,000. And so it's really great to be in high demand and have a technical education, because they just keep bidding for you, and you just go, hey, you pay me. This is my knowledge. You pay me for my knowledge, and I love it. So hopefully that will be your case in a few years, and you'll be making, probably your first year, $70,000, $75,000, and you'll be going, man, how'd I ever survive as a student this way on $7,500? Now I'm making $75,000. All right, but I digress. So with that in mind, like I said, hopefully you saw the same EMF. By the way, as a side note, especially for those of you becoming engineers, electrical engineers, but those of you who are in the circuits class right now, notice that this tells us something very important, that you should never try to measure a battery and decide if it's good or bad if you're not also drawing current from it. It's called a load test. If you just go, if you think your car battery is not working right. In fact, this I learned the hard way. It was a good lesson, but a hard way. I was a freshman in college. I was learning about this myself, and I went out one day and my car wouldn't start. I got a voltmeter. I thought, hey, I know how to do this, and I hooked it to the voltmeter of my car, and I got 12 volts. And I go, well, it's not the volt, it's not the battery. The battery's good. And I kept tinkering with other things. Spent way too long on it. Called a friend, an older friend, an engineer older friend, who quickly pointed out, he goes, oh, that's not a good test for your battery. You're not testing it while there's current drawing. You're not doing a load test. And tried to explain, and I didn't really quite get it at the time, that you get the same voltage minus how much current and resistance you have. And so if you just go with a voltmeter, the current is so small that you're not going to see much difference. But when you try to start your car, oh my goodness, you're trying to get so much current that if you have some resistance here, because the battery is old, this will quickly drop and your terminal voltage will go way down, even though your EMF is not. And so the way I did it, which would be a non-load test, is I just measured the EMF. And I got 12 volts, and I was happy, and I thought it was something else. But he told me, go out there again with your voltmeter, and this time I want you to turn on your lights. He goes, or try to start it, but just turn on your lights, because it's hard to try to start it yourself and look at a voltmeter. He goes, your lights, turn on all your lights, and they carry a lot of current. And if that voltage goes down, that is going to tell you that you have a lot of internal resistance in your terminal voltage. So sure enough, I went out to my car, and I turned on the lights, I hooked up the voltmeter, and I got some pathetic reading like 5 volts. I turned off the lights, and it went back up to 12 volts. And so I learned, and I'll call it the hard way, because it took me many hours to actually learn it, but you know what, I've never forgotten it. And it stuck with me, and so it made me that much better as an engineer when I was working for Boeing, and I'm probably that much better as a teacher now that I'm teaching the science, because I learned it. I learned it in a way that I will never forget it. And that's what I'm trying to get across to you, is that this then needs really a load test. Otherwise, you don't really know if it's a good battery or an old battery. And so I'll say it again, this is our step 2. This is our illustration that, notice, an old battery and a new battery gives us the same EMF. You can't really decide if your battery is wasted and dead or still new and good until you test it under a load. So with all that said, let's get to the hardest part of today's lab. and to illustrate these batteries, as well as the homemade voltmeter here, or potentiometer, in number 3. Number 3 says, determine the terminal voltage when you are under a load, when you are actually drawing a current. And so you will hopefully see what I'm trying to convey here as we hook this up. So I will change colors so you can see it a little better. Maybe I'll go to green. But I am going to run an experiment, and then I'll talk about the theory behind the experiment. And if you've already read those first pages, maybe you got the theory already. But I'm going to hook up something. And so I'm going to put in green some wires with a resistor. Let me call this capital R. This is what I'm going to refer to as the load. I'm going to actually hook this battery to a load and then see what the voltage is. And I'm going to do many different loads because as the load changes, it would draw more current. So my resistor, and again, not showing it real well, I probably, if you remember from last week, had individual resistors. I had the blue ones and the red ones, and I just held them in my hand and I was showing you what they look like. If you took this cover off, you would see hundreds of them in here. Actually, you would see 10, 20, 30, 40, 50, 60 of them in there, okay? And these 60 resistors here are designed this way, that by turning the knob, I can run the current through a whole series of these resistors. And so this is called, you can see the name, decade resistor box. It's called decade because each knob controls a factor of 10, a different decade of this box. In other words, this box right here, or this knob right here, controls the ones. This controls the tens. This controls the hundreds. This control, whoops, over here, the 1,000. This, the 10,000. And this, the 100,000. Okay? So the largest this can get is when I set it here at 10 100,000. Well, 10 100,000 is a nice way of saying a million. Okay? And so that's a million. Now, I'm going to put it as a 10 here, a 10 here, a 10 here, a 10 here, and this probably won't be necessary, but a 10 there. Okay? And so this decade box, my load, is set at, and so let me start my measurements here. So number 3, oh, that pole's going to get in the way here, huh? I'm going to need a lot of space, I think. But I'll keep going. Is this, maybe I'll just put it here and then come down. So is that far enough out of the pole way? All right. All right, so there's number 3. And so what I'm going to do is I'm going to start by hooking up. As I said, this is really 1 million. So here's my load resistor, 1 million. This is 10 10,000s. So that's 100,000. This is 10 1,000. So that's 10,000. This is 10 100s. So that is 1,000. This is 10 tens, so that's 100. And this is 10 ones. And my goal then is to say, what is the terminal resistance, right? And of course, we will be measuring this in ohms and this in volts. All right. Now, I would say that that is a lot of resistance. And so when I first hook this up, coming back to this picture, I would say I'm going to first hook this up, and that resistance is so much that it's probably not drawing much current, and therefore this term is still really small, and therefore my terminal voltage and my EMF are probably still going to be very close the same. And so that's kind of my first guess. Let's see what happens in a moment when I hook it up. But then here's what I'm going to do. I am going to turn the knob once and drop this down. And so let's see. So I will have dropped to well, I guess I drop 100,000, right? So I guess I'm there. Then I'm going to turn the knob again and drop another 100,000. And then drop another 100,000. And then another 100,000. And I'll keep doing this, although I don't think we'll see much effect yet. And so this is the part I was saying is kind of the main step here of the lab. So here's the R and here's the V. And so I'll go to 311,000, 211,000, 111,000, and then finally 11,110. Okay? Now, things will start to happen at this point, and so I'll start turning this knob, which is the 10,000. And so, I messed up. Sorry. That's as low as I can go. So when I go to this knob all the way down, I still have the 100,000 from this one. Okay, so then I'm going to turn the knob one click and go down 10,000. So this will be from 11 to a 10, then it'll be a 9, then it'll be an 8, and then a 7, and then a 6, and then a 5, and then a 4. Whew, I told you, it's going to be a lot here. And then a 3, and then a 2, and then a 1. And so when I get all the way down to there, I will have the 10,000 from this one, and then 1,000. All right. Then I will start clicking again, going down by 1,000. So this will be 10,000. This will then be 9,000. This will now be 8,000, 7,000, 6,000, 5,000, 4,000. All right, keep going here. Whoops, I bumped this. You still got my sound? I hit this kind of hard. Okay. And then keep going. And so then I have 3,110, 2,110, 1,110, and I think that'd be the end of this knob there. And so maybe just a little bit more, just because I know from experience that this is about the end of where we can go. So I'll drop it by 100. So this will go to here. This will go to 900. This will go to 800. And that's probably where I'll end up stopping, somewhere in that ballpark. If I keep going, I'll let you know here. But let me just make the rest of the chart here available. And since we've got a lot to measure, and most of the change occurs when the load starts getting low enough that we can get a significant amount of current. I'll do the first set of numbers kind of quickly and see what we get here. But let me just say it again in case I didn't get this across. Here is the whole idea that you are going to hopefully see that the voltage I measure on the terminals of the battery is going to be decreasing because of this factor. It's going to be decreasing because of the internal resistance. And every battery has an internal resistance. I'm just going to be using the old battery because it has so much internal resistance that we can see it. With the new batteries, the internal resistance is so small that we would have to turn this down so much, we would get so much current, we would burn up our resistors. And so we don't have the equipment designed to measure the internal resistance of a good battery. We can't do a load test on a good battery. It's why we usually take these down, and especially the car batteries, we can just go down to Pep Boys or Kragen and just have them put them on their load test. And I got the little workbench, you put them there and you hook it up and the little meter says 12 volts. And then I'm saying, then you close the switch, which is like turning on the lights or trying to start the car, and then you watch that voltage. And if it goes way, way low, you know you have a bad battery. And so that's why they offer that load testing there for free, so that they can sell you a battery when you walk in there and go, okay, it's not working right. Okay, so now let's actually hook it up. And so, as I said, these green wires would represent this. And so let me grab two wires. I don't really have green ones, so I'll just make these two wires represent my green ones. Now that I played with the knobs a little bit, let me go all the way to my starting point right here. And let me point out then that here I have my load. And so here's the battery, and you might say, okay, I'm running a circuit here right now. I have actually a I don't know if you want to call it a light bulb here. There's so much resistance. So let's see what kind of voltage do I get with my homemade voltmeter. So I'm going to go ahead and go 1.59 and tap it, and it doesn't really budge. All right, so now let's record all this. So step 3 is a long step. We got a lot of recording to do, so I will begin. And so I've got this set on 1,111,110 ohms. And so let me give it a try here. And so I'll make a connection here and adjust. And I have a feeling that it will not move. And this is such a high resistance that it is essentially the same thing. It's like having no load hookup. In fact, I don't think it'll even change much within this whole first knob. So let me go to the next setting and see what happens. And I might, for the sake of speed, just kind of test, does it change? No. Let me go to the next setting. And there we go. Does it change? I'm going to say no. Go to the next setting. Does it change? I'll say no to that. And so just save me time from walking over there. Next setting. No, still doesn't change. Next setting, which I'm on 5 on this dial, so I'd be at the 61111. So over there on the 611, I'll push this and make an adjustment. Did it change? No. And like I said, I don't think we will be drawing much current for a while here. We're at such a high resistance. Still no change. Let me go to the 2 on this setting. And maybe a change. Let's see what the 1 gives me. Okay, let's call that 8.5. So let's see. So I'm on a 1 here, so that'd be a 2 because I add that 1, and because that'd be 100,000 and then another 100,000. So that the 200,000, we get to see some change. All right. So finally, this is about a 1.585, and this was about a 1.589. Where all these other ones were still 1.590, 1.590, 1.590, 1.590. And hopefully then you're seeing that the terminal voltage really hasn't decreased, but it's beginning to decrease. This is the part I was saying in here, where we are going to see then the drop of the terminal voltage because we get the energy from the chemical reaction and then minus a little bit. And so we see that first bit of change. And so maybe there'll be a little more change. It certainly doesn't change by much still. And so we are at 1.1111. Okay, yeah. All right, so let me give it a try and a little adjustment here. Yeah, let me call that an 8.0. Okay, so here's an 8.0, 1.580. Okay. And so this 100,000 will now become, let's see, that'll be 10 times 10. Yeah, so, all right. So keep going here. And maybe I'll call that a 7.8. 7.8. That's a 1.578. And another click here. And not much of a change again. And these aren't even changes like the other one. But didn't change by much. Got a little nervous there. Let's see what we have again here. Come on. Be nice. Maybe right about there. Okay, 7.5. Okay, so I think I'm seeing some changes here. Hopefully we'll get a nice looking graph. We'll talk about that, but I'll try to go fairly quick. Okay, come on. Not having a good luck with this making connection. Okay, there we go. Oh yeah, so call that a 6.9. 1.569. I'll go to another click. A little too far right there. 6.7. Another click. So we should be at the 5.1. Okay, good. Come on. Ah, there we go. Oh. Something about this switch on this galvanometer. Yeah, we'll call that good. Is that a 5.7? Now, hopefully, this will still look like a good plot. It looks like it's a little jumpy on me. I'm not getting the kind of connections that it really needs. I'll push hard and push hard. Yeah, maybe I overread that one. That one seemed too much. And then now, of course, this is a 5.7 also. So that'll be part of our statistical fluctuations here in our graph. Let me go to the next one. We're starting to see a bigger change there. I like that. That was 4.5. So 1.545. One more click there. Oh yeah. Oh good. And this is the main part of the graph. Some significant changes as we get more and more current. That's a 2.5. And so 1.525. One more click on this setting, and so now we should be at 1,000 times 10. That's the 10,000. 10. Oh yeah, and then this one makes 11. Okay, yeah. So we're still on board here. Oh yeah, look at that big change. Wow. Okay. All right, and this would be a 1.468. 1.468. Nice. Okay. And as we'll see in the graph and as we do the theory, it changes the most when we get close to the internal resistance of it. So you could tell that we're getting close to it, or at least within a factor of 10. So probably the internal resistance is somewhere around 1,000 on this one, because we're just 10 times that amount right now. Starting to see some significant effect from it. All right, and so, ooh. And so this is, and our changes are different, so I guess that shouldn't surprise me. 1.457. 1.457. Okay. Next little click. .4, must be 442. 442. Next little click. Uh, 428. 428. Next little click. Uh, 407. 407. Next little click. I should have made my table closer so I don't have to keep walking so far. 380. Next little click. And of course now we're really seeing the terminal voltage change. 345.1, and seeing the changes with my little homemade voltmeter. I like it. Come on, there we go. Good connection. Come on, come on, come on. Okay. Let's see, 43. So that'd be 300 even, huh? Okay. So 300 even. All right, a couple more clicks. And so I'll click it here. And let's call it 225. 225.1. Let's go with another click. I might need to spin this around so I can get closer. Oh, too far. And 1 point, that'd be a 1, but not a 1.102. So 102, 1.1. Good. Next click. Next click probably puts it on less than 1. Somewhere about here we go. And so that would be 870. 870. Wow. 870. That was a big change. 0.870. Let me just double check that. That seemed like a big change, but we went to into that setting. Yeah. Okay. And so we should be at the 1000. Okay. Now click. All right, let's try that one. Nice. Okay, and so this should be 833. And I think that might be, as I listed on the board, I wasn't sure if that would be a good place to stop, but I think we got enough to get our curve fit and then find what we're going to find, which is that internal resistance. So this is 791. And so 791. And I think maybe our last one might do it. Yeah. Because they say go down until you start getting things under 0.75. And so we are at 746. And so 746. Ah, yeah. Okay. Now, let's talk about the theory behind it. What I need you to do, though, and this will probably be the most work for you, other than watching this lengthy lab, is you need to type these in. We're going to make a graph of these. We're going to do a curve fit because I claim that there is a pattern here, and maybe I'll try to squeeze the math in, right? Well, no, I'll just come over here, so it'll be a little bit out of the way. But if you think about this circuits we're doing, that, and I'm just going to put the circuit back over here where my green marker go. This is my battery, and what I've done is I've made it go through this this load resistor that kept changing. Let me throw another little symbol at you. If you draw an arrow through one of these symbols, like the capacitors or the power supplies, that means they're adjustable. Okay, so that's really what I have, so I could adjust my load. And of course, as you just saw me do, I adjusted it from a very lot of a load, which meant very little current, to something that was not very big, or at least it was small enough that we could begin to see the effect of the internal resistor. And so let's just apply our Kirchhoff's law here and say, all right, if you go around this loop right here, if this is your EMF and your current is I in this circuit, then you have an increase of E, the EMF, script E. You have a decrease of IR, and you have a decrease of I capital R, and that should equal to 0. So the sum of all the voltages around the loop should equal to 0. Now, solve this equation for the current. So I'm going to bring these two to the other side and then factor out the I, and then have my EMF over here. And then if you bring the little r and the big R, this, and divide, you have an equation for the current. And that's here for a moment, but this is what I was trying to get across. It's a little on the low side. Still picking me up?
A little squealing
there. Okay.
It's okay, it's still here yet.
All right, yeah, we're almost done here, so we'll see if it lasts. Okay, so this is the current, and if I wanted to then know the terminal voltage, the terminal voltage would be the voltage from here to here. So we could write it as EMF minus IR. So let me do that. So this is EMF minus IR. And as we just said over here, the current would be the EMF over little r plus big R, and then of course times that little r. And so if we simplify this with a common denominator, we would get ER plus E capital R minus E little r. The little r's would cancel off, and so we'd have script E capital R over R plus capital R for the terminal voltage. This is the part at the beginning of the lab I said that your author, I think, does a good job at the beginning pages, and he goes through this analysis and he says, if there is an internal resistance to the battery, this should be the mathematical equation between the terminal voltage and the load resistor. And that's what we have over here. So maybe give myself a little bit more space. Here is the big step for you to do at home. That is, enter this data into, and I'll let you pick whatever you want, like I did last time, although I'm going to recommend graphical analysis. Go to the virtual machine and use the graphical analysis. If you need any help finding the virtual machine, well, I have some instructions I can send to you, but I know that the tech people sent it to all you students, and I kept a copy in case anybody had trouble. But like the last one, go ahead and make a curve fit. And graphical analysis just seems to be the easiest one. I noticed though a bunch of you did do, some of you did Excel, some of you did Google Sheets, and either one's fine, but you do have to do a curve fit. And I'm not real good at curve fits in those other programs, but graphical analysis I am, and I know it's really simple. So that's what I will recommend. But what you're going to then do is plot the terminal voltage on the vertical axis. Okay, so put in these numbers, what we just measured, put in the terminal voltage. And on the horizontal axis, put in the load resistor. You see, our theory says it should follow some kind of pattern like this. And this doesn't have a nice mathematical name, and the x's, if you will, if you think of it this way, y equals, have some kind of constant times x over some other constant plus x. You can see that for small values of x, this one rules, and this one can be ignored, and so it's linear, so it looks something like this. For big values of x, you can see that we can ignore that, and then of course these would just cancel off, and you would have a constant, and so it would do that. And of course, in between values of x should morph into it. And so hopefully you see something that looks like this. That's what the theory is saying. And so the theory is basically saying, if you have, and I'll put a little line right here, large load resistances, then your terminal voltage is basically your EMF. But when your load gets below a certain value, and as I said earlier, somewhere around about 5 to 10 times the internal resistance, you'll be seeing it dropping off. Your graph will probably go right about here, because this is about 1.5, and I collected data to about 0.75. And so your graph isn't going to show this part of our analysis of our graphs. But you should have this. And here's what you're asked to do then, is you're asked to curve fit this. So if you're using graphical analysis, and you've done the curve fitting before, know that a lot of times in the past, we would just scan down that table and find the one we want, like linear or quadratic or exponential or logarithmic or whatever. This doesn't have a fancy name. This you will not find in the chart. So you have to go to the button below the chart that says define your own. So type in this, type in the function a, and your computer will interpret that as a constant, times, and it may give you an r or an x. You can look on it and say, okay, is it plotting an r on an x? See, you decide that, because if you come back over here, and if you just use the default, which calls the first column an x, then you need to type it as an x. But if you change your x to an r, then you need to change it in defining your function to an r. Okay, so I'm going to pretend that I changed it to an r, so I need to type in an r so the computer knows what I'm talking about. Then if you type in a b, the computer will know you're talking about a constant, and then your r. And so that's what you type in. So type that in, and when you do, it will give you a little box and the curve fit. Maybe I'll change colors, but it'll give you that curve fit right over the top of it, and it'll say in the box what the value of A is and what the value of B is. And hopefully then your value of A is in agreement with the EMF, which we got as about 1.59 for this battery. And also, though, here's the big one. The value you get here for B is what we're looking for. This is the internal resistance. So that's why it's important to put that data in and do the curve fit, because our goal here is to find what is the internal resistance of this old battery. And I don't know what it is. I haven't done the graph, so you guys decide. But just looking at the numbers, I'm guessing we're around 850. How do I know that? Well, I'll give you a clue. If your load and internal are the same number, then there would be 2 of these and 1 of those, and you would get half your terminal voltage. So if you come over here, where did I get half of my terminal voltage? Somewhere between 910 and 810. So your internal resistance on this curve fit is probably going to be very near 850. And so that's the clue I see as and here I go, I get to say it again, read the math. So When load and internal resistance are the same, my terminal voltage is half of my EMF. Now, before I leave you, and I know I've talked for a long time, there are a couple of discussion questions, and I just want to make sure you're ready to answer those. And so besides turning in this step, which you just kind of have to fill in, you watched me do it, but the big step you have to do is this graph, so step 3, then answer these 3 questions. The first one says, what is the advantage of using a potentiometer rather than a voltmeter? And I touched on that, but I'll repeat it here again. Right? The potentiometer measures the voltage when you are not drawing any current. We call this a null measurement. Okay? That's the big advantage. 2 says, what is the distinction between the EMF and the terminal voltages? When would they be the same and when would they be significantly different? I think I answered those. So I'll say no more right now and let you write down the answer to that. And finally, the last part, it says, sketch your graph of your terminal versus load. Explain the shape of the graph and describe how it is used to determine the internal resistance. Let me just say, since this was written before we had the computers and you're doing it on a computer, you don't have to hand sketch it, okay? You're going to make a PDF out of it and turn it in Canvas, okay? But I do want you to answer that last part, is, what is it? It says, describe how to use this graph to determine the internal resistance of your cell. And I gave you 2 options. One was the curve fit, which is probably the more accurate one, or the rough, easy one is what I did. When the terminal voltage is half of the EMF, then these 2 must be equal. And so that's kind of a quick and dirty way. And to be quite honest, when I was working at Boeing, that's how we would do it all the time. We didn't bother to take all this data in all this time. We would hook up the batteries, we would adjust it, we would watch until the terminal voltage went to half of it, and go, okay, that's the internal resistance. And is that good? If we work with that, can we design around that? All right, well, with all that said, I'll call it quits, and that will be this week's lab. Take care.